The nervous system controls everything we do, from thinking to walking to breathing. It works by receiving signals from different parts of the body, processing the signal in the brain, and sending back out signals to tell the body how to respond. So how does the system of sending and receiving signals work? Well, at the center of the nervous system is a special cell called the neuron, which helps transmit signals efficiently and effectively across the body. Dendrites are branching extensions at the top of a neuron that receive information from other neurons and then transmits that electrical information toward the cell body. Dendrites can receive two different types of signals: excitatory signals, known as EPSPs, or inhibitory signals, known as IPSPs. These two signals, depending on their quantity and timing, determine whether or not an action potential will be sent down the neuron.
Like every other cell, the neuron has a cell body which contains important organelles like the nucleus and the endoplasmic reticulum. The organelles contained in the cell body are important for helping the neuron grow and divide. While the cell body does not directly help with signal transmission, it does help produce precursors of neuropeptides, which are important for sending information to the next neuron.
The axon hillock determines whether or not a cell will fire an action potential. To clarify, an action potential is a depolarization of the neuron that sends a flood of positively charged ions through the axon to the synapse. Typically, the resting potential of a neuron is negative 70 millivolts. However, if the axon hillock receives enough excitatory signals, or EPSPs, to reach the threshold point, usually around negative 55 millivolts, it will trigger an action potential. However, if the axon hillock does not receive enough excitatory signals or receives more inhibitory signals, or IPSPs, it will not trigger an action potential. As a note, action potentials are considered all or none events. That means there is equal and consistent strength in every action potential. The axon is an elongated fiber that stretches from the cell body to the axon terminal and transmits the action potential. As a flood of positive ions travels down the axon, voltage-gated sodium channels let in more sodium cations to continue the transmission of the action potential.
The synaptic cleft is the space between the presynaptic and postsynaptic neuron. Within the cleft, there are many processes that occur in order to support neuronal communication.